Hi, I'm Chava one of the authors of UDCT, Unsupervised Data to Content Transformation with Histogram Matching Cycle-Consistent Generative Adversarial Networks. This is a paper we published in bioRxiv that allows you to turn biomedical data into a segmentable data by just producing synthetic-looking datasets. And in this video, I will detail how simple it is to set up to create these synthetic data sets with Python, with a simple Python scripts. And the example I will be focusing on is how to create these data sets for the live and dead images of the neurons. The code is accessible on our GitHub page on UDCT GAN, and let's jump right into it. So I'll just start up a Jupyter notebook, and so the first thing that we'll do is just import a few packages to work with. So I'll import NumPy to handle numbers. I'll import matplotlib in order to display the data. I'll make it inline to see a bit what's going on. Image IO is very useful to load and save data. And for now, this is okay. Maybe the OS for traversing the paths. And the first thing we will do is to just define the size of the images that we want to use. So we will make square images. Let me call n pixel the size of the images, so that an image is then, for now, just a black image. So here I create an image which is 256 by 256 pixel that has 3 channels. There can be more channels, there can be just a single channel, it doesn't matter. This is just for convenience. It is easy to display images with 3 channels in a colored fashion. So for example, I can display this image, which is a black image, and we'll get to how to make images that look like the ones in the paper here. So what we'll be focusing on is how to make the cell bodies, so the green ellipses and the black ellipses, in order to create a synthetic data set that allows us to analyze without having to do human labeling images such as these. So the first thing that we want to do is to set up elliptical objects in our data. So the most important message in how to setting up these datasets should look like is that there should be some amount of variability in the shapes that we create and in their color code, in order to give the Cycle-GAN a lot of variation to work with, in order to map the features that we created onto the actual objects that we want to detect, which in this case are the cells. So one easy way to operate with this is just with mathematical operations. So for example, what we want to do is to create ellipses at a given point in the image. So for that, I will just create a grid with the mesh grid function of NumPy, and the grid will be 256 by 256. And what this gives us is, for example, the XX coordinates. So you see this is an image where every pixel contains the X coordinate of that pixel. So this is all the 0, and this column is 256 pixel, and conversely the Y grid contains the Y pixels. And so for example, if we wanted to make a circle centered, let's say, at in roughly the middle of the image, then we can simply create a mask that tells us where the circle is, and with the circle radius we would just say circle mask is XX minus the origin squared plus the Y, and if this is smaller than the radius square, which let's say 10 pixels, This will give us all the pixels which are located within a circle of radius 10, located at 150, 150. So if I plot this, you can see the circle at 150, 150, which is the mask. And so the point now here is to maybe not do a circle, but an ellipse, something a bit more complex, because the features seem a little bit more elongated, these cells. The circle might be enough for the dead cells, but not for the live cells. We will just introduce enough variation that it looks to us like the original images. So what we will do now is because we don't remember exactly how this formula would look for an ellipse, we're just going to go on the Stack Overflow and look for equation of an ellipse, maybe a rotated ellipse. Maybe this, not this one, but this one. And so we just want to implement this formula. So this is the same as a circle, but it's a general rotated ellipse with different axis lengths. So this is going to be the one axis and the other axis of the ellipse. And so let me just put this out of the window. And let's define. This is going to be a function that takes the image as an input, and it will put an ellipse at some given location. This will be the location of the ellipse, and the x-axis, so the long axis will be axis 1, the short axis will be axis 2, and the angle by which we rotate it we just call angle. And this should be enough for the all-purpose image. Let's also put the grid as a parameter that it takes in. And now we see the formula is simply x minus the x location of the center and y minus the y location of the center times the sinus and cosinus angle. So just to have a shorthand notation, let me just make this window smaller and this one bigger. So we'll have x is going to be xx minus, so this would be the h variable, y would be y minus y, just shorthand notation. So the angle is easier to write in degrees usually, so I just convert to radians. And let's just have a shorthand notation for the cosinus. And a shorthand notation for the sinus. And then the formula is simply x times the cosinus. Let's put it in the field of view. Plus y times the sinus. All this squared divided by the x-axis scale plus x times the sinus minus y times the cosinus. And if this all is smaller than 1, this is going to give us all the pixels which are, let's just return the mask. We don't have to modify the image. So we make the ellipse, and so if we say make ellipse at x30, y80, which is 10 by 5, so rather a flat ellipse rotated by 45 degrees. This gives us a mask where we should have an ellipse somewhere. So the rendering is not great. Let's make this bigger. but we clearly see that it outlines an elliptical region for us to make our cells. So this is great. Now we have the choice how to color these ellipses, and I'll get into how the coloring works in a minute. What we can also decide is whether to have overlapping or not overlapping cells in the image. So the way we could do this is to say, if we make many cells and we want to do this randomly now, we can just say we take the original image and we want to put n cells inside. Then we will randomly choose the locations of the ellipse, which is going to be 256, about the size of the image. So we define this as n pix. Let's just see if this works. Yes, it does. So the rotation is going to be 360 times a random number. So we have a randomly rotated ellipse. The axis, we can decide to change them later, but let's make the big axis 8 plus between 8 and 10, just randomly chosen. The smaller axis, let's make it between 5 and 7.5, whatever. And this is about what we need to define the cell. So we need the angle, the axis, and the location, which are all just random numbers. And if we just now go ahead and add to an image, this is the mask image, so this is not the colored image. So we just say mask image plus equal make ellipse OX, OY, X1, X2, angle, and if we can still pass this as a parameter, grid. We see that we should be able to here just define a mask image, and of course if we just plot the mask image, nothing happens. But now if we say make many cells mask image, let's say 15 cells, of course we need to randomly choose the origin. And so now you can see that by adding this image, you have here overlapping areas. So the cells are overlapping. And then if we really want just the mask, then we just have to choose those pixels which are bigger than 0. And this will really display a full mask. Okay. Now, if we don't want them to overlap, we can say make many cells no overlap, and it's essentially the same, but now we just make a counter. And we just say counter is equal 0, while counter is not equal to n cells. We randomly select these origins and axes, angles, then we make an ellipse, and we only add it to the mask image if the sum of the pixels in the mask image covered by this new ellipse is equal to 0, essentially saying that there was no ellipse at this position before. And if this is true, we add the ellipse inside, like we did above, and we increase the counter. So again, we can here make a mask with 35 overlapping cells, but they're all overlapping. If I just turn off this, and we can see that they overlap. This you can see by the fact that different colors, so they add up to 2 where it overlaps. But we can also choose to make them not overlap. No overlap. Of course, I made a mistake. Yes, of course, I have to sum. If I sum all of these, okay, and now we can make sure that the cells are kept apart. And the great thing about placing cells in here in this way is that simply the cells that get out of the picture are naturally cropped by this method, so we don't have to really care too much about the borders. It's done automatically. Now, what we want is to color these cells in some way, because the texture of a cell is not a unique form. So if we just had a mask like this, every time the convolutional neural network, the generator, passes over this cell, it would always generate the same exact feature. But we can see here that the brightness is different, the shapes of it are different, the granularity of the cells are different. So we need to give it a lot of variation. And one way to do this, there's many ways. We can just simply make it completely random. So we could just say that this is a mask image, and we have an image which is 256 by 250 by 3. So this would be our image. And then we just make a randomly colored field, normally distributed, with a half a value, the location, the scale is 0.2, and the shape or size would be npix 3, and this would be the colors, and then the image at the position of the mask is equal to those colors at the position of the mask. Oh, but for now it's just not an image. So if we plot, then we have these strangely colored cells, and this might be enough, but we're not sure. We can give it a different structure, and for this I'm just going to make the same type of elliptical shapes, but I will color them sort of brighter in the middle and less bright on the outskirts. And just making sure it's recording. Yes. And so the one way to make this coloring is to just define a two-dimensional Gaussian field, and I will put it in one of the color channels just to make sure that we can separate live cells from dead cells. So for example, we will put live cells in the green channel and dead cells into the red channel. So we're just gonna make a color field. Again, the same principle. We have a location. We have the axes that we operate on. So this is going to be the standard deviation of the Gaussians. Let's say S S1 and S2 just to correspond to the same axis as the ellipse, the angle, and we will have X, X, and Y, Y again are fields. And one way we can generate Gaussian fields is that well, first of all, just make sure we can input the angle in degrees to make things easier. So we divide this up. And then, again, we can have a shorthand notation for the cosinus, for the sinus, just to make things a bit more tidy. We can have, now we can rotate our field and then make a Gaussian out of it. So if we want to rotate the field but keep it at the same location, we first need to center the fields. So xx minus ox and y is yy minus oy. But we want to rotate. So these fields are now centered around 0, 0, 0, in principle, the x, and we can now just rotate them. So with the rotation formula, so the new x position is going to be the centered x times the cosinus minus the centered y times the sinus. And for the the new y rotated coordinate, it's s plus xx minus x times s. So these are our rotated centered variables, and we can also go ahead and scale them. So the way that we can scale them is just to divide everything. So x is equal to x over s1, and y is equal to y over s2. And then we just ask to return the Gaussian formula. So the formula for a Gaussian distribution. So it is minus x squared minus y squared. And if we do this and we just try to plot what the result is, so for now it's just a single channel image. So let's put it in the middle of the image with the first axis being longer than the second axis, rotated by 35 degrees with the field. And so now we have a coloring that we can use to color the cell. Now we have to make sure that this would also correspond roughly to the shape of a cell that we put here. So let's just go ahead and make sure that our ellipse, if set up the same way, would yield the same result. So let's do this. And let's put the cell. So it would be the make ellipse with the same parameters. Make ellipse 150, 150, 15.5. And what we realize is that the ellipse is just off rotated by 180 minus the angle. This is probably just a mix-up of around the axes. So let's just try and correct that. So I think if we do this, I think it should work. Let's check. Yes, so now the ellipse and the cell seem to be rotated the same way. Okay, so this is now, we can use this field to color the inside of this cell. Let's just check again. And if we make it bigger, so the same axes are scaling. Yes, okay. And the good thing is that the color field is contained between 0 and 1, which is quite important to create these color images, which we then will scale to 8-bit so that we can save them in PNG format. Now, we don't want to have always the same brightness. So what we can do is to say because the maximum of this color is going to be 1, we can just scale it by a factor. So we give it a constant brightness, for example 0.7, and we add 0.3 times this, but 0.3 times a random number. So this will color the cell with base brightness and then some Gaussian variation on top of the cell. So let's see how this works. So in this case, it is quite bright, 0.9, 0.9 still, 0.8 now. Okay, so we have these variable colors, and let's see how it looks like if we make cells to be the same color. So yeah. So these numbers can change, of course. What you can see in the supplementary information of our paper is that it is basically important to have some level of variation. It shouldn't be always constant, otherwise the generator always produces the same images, and we want to maximize the versatility of the shapes it can produce, so there has to be some kind of randomness inside the cells. So this can change to many numbers. Now the only important thing to think about is that at the end, because the background is all black, we also will have to add some noise to the background so that the network can reproduce the background from that noise of the real images. And we just want to have color levels so that we can separate the background from actual cells that are detected. So usually we put this number quite high with some variation, such that we can then separate it from the background in a later stage. So let's just tidy up. Let's put that definition on top. And now the mask image can have many dimensions. So here what we want to put, for example, if we allow the overlap, is that this will be a mask, and then we will put into the image the color field in a 3-channel image. So if we now accept that the input image has 3 channels, then we go every time we produce a cell, we have the random positions and rotations and scales. We have the mask of the cell. This is where we want to put a cell. The color values are going to be the Gauss color with the same exact variables. And now what we put in the image at the mask cell position, and now keep in mind that the coloring of the images is red, green, blue. So the second, which is the first index channel, is the green one. So in this one we put color values of where the ellipse is, and this is just a single channel color. Now we can do the plus equal operation on top of it, and then at the very end, then we just have to clip the image so that every number be above 1 is clipped to 1. So image 0 and 1. Okay, so now if we plot make many cells, we give the input image that we created up here. We want, for example, 15 cells with this field. Obviously there is a mistake. So yes, I cannot call this image, but it is mask image. This is the input variable. And now if I plot my image, which I will have to redefine, it has this it has these cells which have a random coloring on them. And if you want to see it a little bit better, then you can just make just this coloring. Of course, I have to remake the image. And now you can see that some problems occur at the clipping points, but we can, for example, choose to not clip this and just not have the plus equal sign. So now the cells are not are just printing on top of each other, which makes them separating the cells a little bit challenging. Of course, we can do the same here by saying that, okay, here also to keep in mind that the input image has 3 channels, and we say the same thing. So while there isn't the amount of required cells, keep going. And then we have the ellipse is basically the mask. And so we say mask image at the position of the ellipse. So here it is important to say the mask image has now 3 channels. So if in the first channel the region captured by the ellipse mask is equal to 0, then we can add the ellipse because it doesn't overlap any other ellipse. And then we just add the Gauss color at that position. And so if we check, this should work and we shouldn't have cells overlapping at all. Now there's different ways of doing this. Now if we like this, we can also introduce more variation in the color, and we can, for example, keep this Gaussian profile and we add on top of it just a normal distribution. So the location of which, so this is the mean value should be 0.15, for example, so that we have a 0.7 maximum value plus 0.15, a scale of 0.1. So roughly the pixels are oscillating between 0.5 and 0.25 on a random scale, on a normal random scale. And the shape or size should be npix times npix. And so this will just pull a random noise over the elliptical shape, the Gaussian shape of the color. And we can make sure that we return something that is clipped. So we clip the color between 0 and 1. And now you can see that the cells are a little less defined. So let me just, so you can see how the noise now enters the coloring of the cell. And of course, if you, this should be good enough. You can decide to make it harder or softer. This doesn't really matter. What really matters is that you can distinguish these shapes afterwards in your analysis, in your post-processing, from the background that you will introduce. Now we want to input the dead cells, and to do that we will do exactly the same, but we will make sure that the dead cells do not overlap with the live cells nor the other dead cells. So in order to do that, let's make them just not overlap. Make many dead cells, no overlap. Of course, the dead cells are smaller in shape with some variation, but just general much smaller, and they are rather round. We can also let this parameter vary, but in general, we just make them much smaller. All of these parameters can stay, so we just put them randomly in the picture. The angle is also random. They are rather round because now the axes are not allowed to vary too much. And we will make sure that when the condition is met, we put them in the red channel. But we also want to make sure that they don't intercept any green cells, but also they don't intercept any red cell. So this is the red cell. So if these both conditions are met, then we can add dead cells. So for now, nothing has happened. We just added the green cells, and we will just add the dead cells. And let's add 25 of them. And you should see this dead cells pop up. You can add 35, and there you go. And now in the last step, you want to make sure that you give some type of noise to your background. So you want this background to not be black, otherwise the generator takes this input field, which is all zeros, and it will just generate the same type of patch from this zero, making it impossible for it to recreate any type of complex background images like here, where you see all this dirt, these axons, and these different things, and different types of focus, different types of illumination. So it really needs a lot of noise, or it needs noise in the background. Now the magnitude of the noise does not really matter, and again, you can check our supplementary info for these details. But the easiest way to do that is to just give it a random Gaussian noise. So again, we just make a random normally distributed noise, give it some base value, let's say 0.1, so log, give it some variation, scale is 0.15, which should, so this noise has the maximum amplitude on average of 0.25. So this is the maximum amplitude it will have. So it should never overlap with the red levels or the green levels of the rest of the cells. We could also put the noise only into the blue channel. We haven't tried that, but maybe this would be the easiest way of separating all the noise from the dead cells from the green cells. But this also works the way we're doing it here. So the this would be just a random background noise. And of course, now we have to define where we want to put these pixels. So you can see that if the image is equal to 0 in the red channel, this takes us all the background minus the live cells. But if we also add the green channel, then you have the whole background lighting up. So this would be, sorry, or. So this is the red. So this is the red and the green, green background. Okay, so this is our mask. So background mask is this. And so now we just add the noise to the image. And the final image, well, has too much noise. Random background. Yes, we have to clip it. We don't want it to be small. So we clip it between 0 and 1, otherwise the rendering has some issues. Exactly. So what happened to our live cells? I don't think that the mask worked too well. Yes, this is not what we want. No, so this was exactly. So this is now our image, and you can see that now this is the noise with the background noise, the red cells and the green cells, and this should be enough for you to be able in a post-processing step to keep these classes away. So just to check if this is the produced output from the network, you can query, for example, all the red patches that are bigger than a certain number, and you can see that still some noise spikes get over the required threshold for you to detect the cell. So maybe you don't want that, and you will just keep the noise a little smaller. Just make sure that the noise is not too small, because then you want to compress this image into the integer 8 to save it into PNG format. So now if I just show the image, this is the image, and it has some background noise, it's enough, and the red cells and the green cells are kept apart nicely and they're not overlapping. So now you can go ahead and just make a function that will generate training data. Maybe whatever number of pictures, and it has to take an image, put some random amount of live cells, some random amount of dead cells, and for example, you can say live cells is anywhere between 13, between 5 and 35, for example, and dead cells is anywhere between 25 and 55. For a study of how the amount of cells that are put in the image influence the end result, you can refer to our supporting info. The main message is that it is not too sensitive, and you can make a mistake of the order of 50%. 50% underestimating or overestimating in both directions. So this would be then the amount of live cells, the amount of dead cells, and let's just we just create a training folder, and once the image is ready, we just scale the image. So the scaled image is to 255 to get the 8 integer. So 250 times the image, and we just go over this for I in range and pix. We create this image, and we just have to then save it with the io-imsave training folder plus string e. You can add zeros to it. So generate training data, 30 pictures, and I don't know where I'm working right now. Okay, so if I go check my home folder, you can see that the images for training were created, and we can create as many as we want. So that was it. I hope this was helpful, and make good use of it.